No.
All right, guys. So we are live now. What we're going to do is we're going to take a look at that half sheet practice that you had on Wednesday night into Thursday. Looks something like this. And then after that, we're going to take a look at the practice Thursday while I was out, which was the full sheet on one side, and you had some more practice on the other side as well. So that's our goal, is to get through all that in class today. When we're done with class, this video will be available on my YouTube channel and on the website. Yes, sir?
Wait, I have a question. For you to test with it, or are you going to give us like those equations? Give us
In years past, Chem 2 gets this,
there's like 7 of them.
and honors, actually there's 6. And generally honors does not get them.
What?
I think that this year.
I think that this year.
That's
a good idea.
Especially because it's right after the spring.
I think maybe I'll do a coin flip and we'll leave it up to chance. Ooh, all right. So you do have these equations that we learned in class last week. Keep in mind that like pH and pOH are very similar. We're just replacing the concentration. And then define our H plus or hydroxide concentration as the inverse log. So yes, you have 6 equations, but 4 of them are really like 2 that are repeated in a sense.
For B, like on the first one, would you like us to write it how you did, or do you want us to put in such scientific notation?
You know, I guess my preference is scientific notation. I know that our calculators aren't always set to be scientific notation, so if you have something like B, you know, it'll go in standard notation. So I'll get what you're doing. So if you guys look at number 1, you're provided with a pH 12.3. You're asked to find the proton concentration, hydroxide concentration, and pOH. So the nice thing about these problems is you can go in any order that you want. And I try to demonstrate that in these problems by going a few different avenues. First, if we're given pH, if we do the inverse log of that, we can find proton concentration, which comes up to 5.01 times 10 to the minus 13. And because it's concentration, we do have to stick in the unit, molarity, molar. And then at this point, you can do either B or C. This morning, they chose to go B. And so we have the H plus concentration times hydroxide equals 10 to the minus 14. So if we solve for hydroxide by using what we found in A, we get, it's like 2.00 times 10 to the minus 2 molar. So it's a pretty high hydroxide concentration, which should make sense because your pH is 12.3. That's not very acidic. It's actually pretty basic. So we should expect that our H plus concentration is small and our hydroxide concentration is larger. And then for C, to find the pOH, one route we can take is we can take our hydroxide concentration from B, plug it in for negative log of that to get pOH, which is 1.7. Or we could have done pOH from pH, where pH and pOH together equals 14. So doing that gets us a pOH of 1.7. And if you wanted to solve B at the end, we could do the inverse log of the negative 1.7, which would get the 0.02 molar that we found in B. So the point of all that is we could go ABC, or we could have gone ACB. The order doesn't matter because in the end, numerically, we end up with the same thing. So I guess that goes to show that I don't really have a preference as to which one you did, as long as you did it right and got the right answer. Okay. It's kind of the beauty of pH is that we have those multiple avenues to go down. Okay. Any questions with number 1? All right, then here is number 2. So 2, they gave you a proton concentration, bless you, of 2.8 times 10 to the minus 7. And you were asked to find pH, hydroxide concentration, and the pOH. So in this example, when we did this first hour, they said, hey, let's find A first. Because you have proton concentration and pH. That came out to 6.55. And then if we do C, the pOH, we just have to subtract it from 14 to get 7.45, which is our pOH. And if we take the inverse log of that negative 7.45, that'll give us a hydroxide concentration here of 3.55 times 10 to the minus 8 molar. But if you decided to go and find hydroxide first, well, you were given the H plus concentration here, so divide 10 to the minus 14 by that H plus concentration, and that gets you 3.57 times 10 to the minus 8 molar, which is effectively the same as what you found already. Going the other way, I realize that it's 0.0000002 off. I don't care. It's a really small difference, minute. Okay? So when you're at 10 to the minus 8, it's not a big difference. Do that value and you want to do negative log of that to get pOH, that would get you to 7.45. So again, multiple ways of solving the problem. Okay. Any questions with 2? Okay. How do you guys feeling about it? Okay. Up until 3 and 4. So with 1 and 2, were you guys okay with this on last week, you think? Because I feel like I kind of rushed you through it, and then I tried to make up for it with the tutorials Thursday while I was gone. And truthfully, I had a lot of faith that you guys would be able to figure it out because you're honors. And if some of you didn't get it, some of you did in the class, and I figured you'd probably find a way to team up and figure it out. At least that was my hope and my expectation. Okay? But we're still sitting down looking at this today because I figure it helps. All right. Let's look at 3 and 4. All right, guys. So here's 3. 3 wants you to find the conjugate acid. And remember from definition, the conjugate acid is the result of the base accepting a proton. So in a weird algebraic mathematical way, the way I look at finding the conjugate acid is I add H plus to the ion. So if we have hydroxide with a -1, and I add 1H with a +1 charge, then the new formula is H2O, and the charge is 0.
Oh, so, okay. That's always add H plus.
What's that, Katie?
Always just add H plus.
For conjugate acid, yeah, it's the base accepting a proton, so we add H plus.
I get it.
So then carbonate here, CO3 -2. Gentlemen. Carbonate, CO3 -2, and we add H plus. Well, there's no H to begin with, so now it's HCO3. And then the charge is -2 + 1 is -1. So that's the new formula. That would be the conjugate acid. Okay. I can't think of another way to explain conjugate acid and conjugate base other than just go by the definition. You know, conjugate acid, the base accepts a proton, so we add a proton to the formula. Okay, for 4, the conjugate base, remember the conjugate base is what's left when the acid donates its proton. So if we're losing a proton, just subtract or remove it from the formula. So if you start with NH4 + 1 and we remove H + 1, well, now the charge should be 0, and we have 1 less H in the formula, so it's NH3. Okay. In B, we started with HSO3 -1. If we remove a proton, Well, now we lose an H, so we're SO3. And charge, we were -1 minus 1, which is a -2. Jeremy.
Why did your charge go away?
You were NH4 +1,
Yeah.
and we subtracted H plus 1. So the ones go away. So like it's kind of like that algebra way where we do the variable subtracting, like terms, and then the numerical part is Guys, you guys realize you're on video right now, right? A lot of background noise.
Have you seen Terrio?
All right, number 5, you're given this equation, nitrous acid plus water yields nitrite and hydronium, and you're asked to label acid, base, conjugate base. If we ignore the labels for a moment, it's like, hey, how do we figure this out? I thought acids start with an H. And you're like, shoot, HNO2 and H2O both start with an H. If you're not sure which one is the acid or the base in that side, it's okay to look on the product and identify the conjugates. And that's what I would do here. I'd say, okay, NO2 minus 1, there's no H, so that's probably the basic part. And then hydronium has the positive, more positive character, plus the H is going to be the acid. So there's our conjugate base and our conjugate acid. So by definition, the acid donates a proton and becomes the conjugate base. So HNO2 should be the acid and water is the base. What term do we give to water if it can be an acid and a base?
Neutral.
Amphoteric. Yep. So amphoteric can behave as both. In fact, if we think about it like NH3, it can gain a proton to become NH4 plus 1. It can also lose a proton to become NH2 minus 1. So ammonia is amphoteric. Okay. Up here, bicarbonate can lose a proton to become carbonate. It can gain a proton to become carbonic acid. So that substance is amphoteric. So if it can do both the gain and the loss, then it is amphoteric. Okay. For number 6, explain what happens to each of the following as the pH of a solution goes down. So remember, if pH goes down, we're becoming more acidic and less basic. Does that make sense?
Yes.
I said the H, the H plus.
Yes. So I covered part of that up. So before I answered these, I thought, well, if pH decreases, we're more acidic, so we should have greater H plus concentration around. So that would go up, which means hydroxide concentration goes down because we're less basic. And then if we remember that pH and pOH equals 14, well, if pH goes down, pOH should go up because the sum is still equal to 14. That doesn't change.
Great, thank you.
Plus, something else to keep in mind is that pH and concentration is inversely related. So if pH goes down, concentration goes up. Same thing with pOH. If pOH goes up, hydroxide goes down. So they mean similar things. It's just that if one goes up, the other goes down. Okay. In number 7, a neutral substance is equally acidic and basic. What does this mean?
It's neutral.
Yes, a neutral substance is equally acidic and basic. What does that mean?
That's 7.
What's at 7?
Both the pH and the pOH.
Okay, so pH is 7, pOH is 7. So if we go a little bit more into this, Yeah, it's neutral. pH is 7. It means we don't have any more H plus than we do hydroxide. Their concentrations are equal. So when we talk about something being neutral, let's talk about it in context of concentration. Their concentrations are equal. Right? pH comes from concentration. Okay. Any questions on this sheet? Okay. And let's take our full sheet out. All right, are you guys comfortable if I just write the answers in here, or do you want to see work?
Go ahead.
I think right answers and then answer
I think
questions.
that so they know what we're doing.
Okay. So for 1A, (3.16 times 10 to the minus 4 molar).
You have to do it in 3.16.
Do we have to do what?
Yeah, the 3.2 is that fine?
Oh, yeah, 3.2 is fine. Yep, I was not recognizing sig figs there. So 3.2 times 10 to the minus 11 if you're doing sig figs. And a POH 10.5. Okay, for number 2. POH comes out to 3.59 or about 3.6. Which means pH is 10.4. And that's your H plus concentration. It was 3.98 times 10 to the minus 11. Yeah.
3.89, but I also use 10.41 and 3.59.
Okay. Okay, so 3.9. It's close. I'd take it.
On the test, do you want us to use sig figs? Or is it kind of like, nah?
Let's be consistent, use sig figs.
Okay.
All right, for 3. I guess I'm not really too sig figs. Yes, no. Because I'd rather be more precise here and say that the pH is closer to 10.1 than 10. Okay. 14 minus that, so this is 3.9. There's our hydroxide concentration. For 4, there's our pH. There's our hydroxide concentration. There is our H plus concentration. Any questions 1 through 4?
Can you do an OH 1, 3B?
3B? Sure. Okay, so for 3B, one way we can go about it, we could do this. Okay, so if we divide both sides by H plus, which is 8.6 times 10 to the minus 11, I get 1.16 times 10 to the minus 4, which is what you came up with. I think probably because I rounded my pH originally. So if I had done minus 10.07, whoa. So if I had not done 10.1, but I did 10.07, that would give us a POH of 3.93. And if we do the inverse log of that, that comes out to 1.17 times 10 to the minus 4 molar, which is pretty close to that one there. So you did it right by the sounds of it. It's just that we had rounded the pH, and so we got a little different.
How do you get 1.3?
1.3?
That's what you have in your answer.
So what I had done was 10 to the negative 3.9. And that comes out to, it'd be 1.26 times 10 to the minus 4, but I had rounded. All right. Conjugate acids, number 5. If we add an H plus, you should have an H4 plus 1. Here we have H2SO4. So here are your conjugate acids.
For numbers, or sorry, 5C, does the H have to be in front?
Yeah, we're making the conjugate acid, and except for ammonia or ammonium, acids will generally have the H out in front. Conjugate base, we take away an H plus. Okay, label acid base, conjugate acid, conjugate base. So there's A. And there's B. Okay. For 8, explain what an amphoteric substance is by giving an example and showing how it works. So what is an amphoteric substance again? So an example would be water. So what is amphoteric mean?
This is that thing where it can act as like an acid and a base.
Yep. So substance can act as an acid and a base. It's not going to act as both at the same time. It depends on the context of the reaction it's in. So an example of water being, if it's a base, then the conjugate acid will be hydroxide. If water is acting as an acid, then it has a conjugate base, that would be hydroxide. Okay, so if we look back up at 7, if we do A, if we do this example here in 5 that we saw, in this case, water acted as a base because it accepted a proton and formed hydronium. Okay, but if it were to act as an acid, it would lose an H and become hydroxide on the product side. Okay, so the conjugate acid on the product, if it's a base, it would become hydronium. And then if it's acting as an acid, we get the conjugate base of hydroxide.
So, amphoteric just means like within itself it has both the like conjugate acid and conjugate base for everything.
It does. Well, it doesn't have that, but it says that it can gain or lose the proton. So it has enough that it can take on another one and become a conjugate acid, or it can lose one and become the conjugate base. Okay. For 9, what effect does changing the pH from 4 to 7 have on the acidity of a solution?
Makes it neutral.
Okay, but if we're going from pH 4 to pH 7, what are we saying?
It's a huge difference in like the decimals. I found 10 to the negative 4 versus 10 to the negative 7, and it's like.
Okay, so less concentration. So if you go from 4 to 7, are you more or less basic?
More basic.
More basic, and I meant to say acidic, so more or less acidic.
Less acidic.
Okay. Because it asks about the acidity of a solution, so it's less acidic. Okay, as pH goes down, you become more or less acidic?
More.
So the H plus concentration does what?
Goes up.
Hydroxide?
Goes down.
POH?
No.
Thank you. Okay, for 11, it says using HBr and KOH as examples, write a chemical equation to show how they ionize in water. So HBr in water is going to produce H plus and Br minus. So the fact that it's in water and it ionizes means we're producing those respective ions. KOH in water is going to give us potassium ion and hydroxide ion. Okay. For 12, explain how NaOH and NH3 can both be bases according to our definitions. Well, if NaOH goes into water, we can dissociate into sodium and hydroxide ions. Which definition are we using when we say that in water we produce hydroxide ions? It's a base.
No, say what?
But which definition of a base? Look back at your notes. There are two instances of a base and we labeled them two different terms.
So, oh, there are Arrhenius.
So the Arrhenius definition says that in water we produce hydroxide ions.
Okay.
NH3 when we put it in the presence of an acid, it's going to produce the conjugate, the base will form the conjugate acid, and then the acid would lead to the conjugate base. So the fact that we can do conjugate acid-base pairs, and we show that the base accepts a proton, means that we're looking at the Bronsted-Lowry definition.
Oh.
You do need to know those terms and definitions. In 13, we're actually going to talk about that tomorrow. So we'll skip 13 for now.
Do we ever work together?
Nope.
Alright.
Can I turn the page over?
Go ahead.
Remember, we are making a video right now, so this will be up on YouTube in a little bit.
I'm gonna watch it.
From this morning? You watched this morning's already?
Yeah,
From first hour?
yeah, because I had a appointment at 9, and Mom said, so when I woke up, I'm like, since I watched it, I'm like,
No, I'm still sick, so I figured if I did video first and third hour, then the rest of the day, I could just play the video. All right, listen up. On the back side, you had to do some calculations. So pH for 75, negative log of that. So A is 7.77. B should just be 7. C is 5.66. And D is 3.13. '77, calculate hydronium for each of the pH. This is where we're using inverse log of the negative pH. So for that one, in scientific notation, 2.82 times 10 to the minus 9 molar. Tenth place is fine. .35 times 10 to the minus 3 for C. So I've got all these in scientific notation because the first ones were really small and I switched my calculator to scientific notation. So you get them for all of that, I guess. C and D you could put in standard and that'd be fine. But as you start to get to a smaller number, scientific notation is the way to go. Okay. So 79, calculate pH when you're given hydroxide. So I think what we're going to end up doing is hydroxide to pH, or I'm sorry, POH, and then to pH. So negative log of that value pH of 7.28. .86. Okay, and what I'm doing in my calculator here, you can see it a little bit, is for, let's say D, negative log of 9.5 times 10 to the minus 2 equals, that's the POH. And if I'm being lazy and I'm just subtracting 14 and ignoring the negative, because it's not going to be a negative pH. But pH here ends up at 12.98. Based on what I got on the calculator. Okay. And then for 81, we're given pH, so probably the best way to go is pH to POH, and then to hydroxide. You could also go pH to H plus to hydroxide, but then you have to deal with more exponents. So if we do the inverse log of the negative pH, 4.25, nope, I don't want to do that, that'd be the H plus. So 14 minus 4.25 is 9.75 for the POH. Inverse negative log of that answer is 1.78 times 10 to the minus 10 molar. For C, we get 3.16 times 10 to the minus 13 molar. And the very last one in D, 14 minus 8.25 gets you 5.75. And if we take the inverse log of the negative answer, we get 1.78 times 10 to the minus 1, 2, 3, 4, 5, minus 6. So that's the answer that we get there. Guys, have any questions with the final minute of class here today? Okay. Yeah, thanks for watching. Make sure to smash that subscribe button, like the video if you liked it, for an awesome, boring 40 minutes of video. No giveaway. No giveaway for you.
Yeah.